6.4 Interpreting Statistical Summaries. So this lesson is more about um, how do how do you take data and write reliable conclusions rather than doing more any more calculation work in this chapter. So all the calculation work, the kind of concepts on data analysis have already been done. So now it's about the data. Is it reliable? Can it support a valid conclusion? Okay, so a valid conclusion has to be supported by unbiased data. Okay, and we're talking about bias in terms of your sampling technique and as well as your the way you gather your data in terms of the surveys that you do. Okay, so it's supported by unbiased data that has been interpreted appropriately. Okay, so not only do you have to just make sure your data is unbiased, but have you interpreted the data appropriately? Okay, and this could mean use of your analysis techniques and trying to draw conclusions from those from those results from that data that would make sense, and shows any kind of correlations. You don't want to be connecting variables that don't make any sense, right? They have to be some kind of logical reasoning behind it. Okay, so data, reliability of data. So is data reliable? Well, the data is reliable if the results can be duplicated in another study. This is very common in academic circles, where if you want to verify another researcher's results are true, then that researcher should be able to provide the data in such a way that uh, it can be duplicated. Like, can someone else conduct that same study, conduct the same survey, sample it the same way, and get results that are duplicated? You know, uh, that way you can support that and duplicate it to the degree that solution can be supported, or that conclusion can be supported. So data is valid. So again, so data reliability versus validity. So reliability talks about duplication. Validity would refer to does that data support your entire population? So if the results accurately represent the entire population, right? So what good is it if you're talking about data that you collect from, let's say the Facebook that collects data from its users? How can you cannot take that data and in turn represent and say that, well, this is the same habits that people click on, they like something, right? So let's say, oh well, there's all these different trends of people liking certain things. Well, can that be the same? Can that data be applied to, let's say, Instagram, right? No, like Instagram may have a different set of population for its users. So I mean that's just one kind of example. There's many different kinds of examples throughout different kinds of um, uh, topics of study. So when you read a conclusion someone has made based on statistics, you must decide whether it is valid or not. So to do this, you have to ask yourself, is there any bias? It's really one of the most important things. So so bias itself, there are different kinds of bias you can look at. So how is the sample collected, or how is the sample selected? So that's one way to check for bias. So how was the sample selected? And was it selected in such a way that could introduce bias? Were the questions phrased correctly or phrased in an unbiased way? And was the survey conducted, or were measurements taken? And part of the uh, validity of the data, or the way it's shown, well, the graphs. How are the graphs drawn accurately, and or do they mislead the viewer? So there's different ways you can introduce bias in the way you show your graphs to the person who's reading them or viewing them. When you compare data values, it is possible to draw conclusions based on the results. There may or may not be a relationship between compared values. In many instances, graphs provide stronger visual evidence of the conclusion. This goes back to my point earlier I made in the course, where We like to see things visually more than just putting numbers on a page. Different types of graphs may be used to represent the data. So a multiple bar graph is one type of graph that can be used to represent the data. So an example of that's on the side here. So you have different frequencies for different groups being represented by the different colors. So blue represents the group of people who like music CDs, and red are the people who are in the books. So here in my note here, I'm going to say that frequencies, we have different frequencies for different groups. Are represented by different colors that are placed side by side. Okay, and they remove the gap width for continuous data. So you remove gap width for continuous data, which essentially is like a histogram. Here it's a categorical, it's by months. So they have the different bars separated, but they put the blue and red bars beside each other just to compare and contrast the different kinds of groups. But they all talk about the same thing, month to month to month, the number of books in Lisa's collection. And just for reference, in Excel, this is called a clustered column graph. We also have a split bar graph, which are, so here's the split bar graph where the frequencies for the different groups are represented by colors placed on top of each other instead of beside each other. So girls and boys. And why it may be better to have them on top of each other, stacked like this, is so that you can see the totality of both the frequencies of each individual gender. So pink and orange, or pink and red, orange, or peach, I don't know what you call this color. When I add them together, I get the total number of students. Whereas if I have them side by side, I can only see each individual gender. But stacking also has some disadvantages. You can't exactly see the number of boys unless you carefully look at the numbers and make it subtract the difference. So there's a little bit more of a thinking process involved to get the exact number of boys. Um, but you can clearly see by the color that one is still bigger than the other, so that's fine too. Uh, Especially here for volleyball, there's a clear difference. So for a split bar graph, frequencies for different groups are represented by different colors that are placed on top of each other. All right, my next one is a relative bar graph, different percents totaling. So here it's percentages here, uh, and they total up to 100% for each of these different categories. So one for each group, the men and the women, and the lengths again are stacked on top of each other. Right, so this is different because it's percentage based, not frequency based, and that's the reason why it's percentage based, because it allows us to see the relative numbers relative to each different kind of group. Okay, and to each different uh, group by colors, so that you can see like the percentage of sports, TV, and dance rather than just the raw numbers. So here I'm going to say different percents totaling up to 100%. So totaling to 100% are represented by different colors the colors for each group, and the lengths are stacked on each other. Okay. Now, it may be in your assignment or in your ISU, you might find that one of these kinds of graphs could be of use. And if you do, then by all means, use it as part of one of your data analysis tools. Um, but if you don't feel comfortable, you don't know how to use it, then don't. Don't try and be fancy. Like, you have to know how to, you know. Uh, I mean, I want you to learn these different kinds of graphs. They may have be of some use at some point. So on your own, at some point, look at some of the practice problems. You'll be given some data and try making some of these graphs on your own on Excel. Okay, so assessing graphs. So statistics are often used to represent certain points of view by manipulating graph axes, by citing one measure of central tendency, or through measurement or sampling bias. It is key to perform a critical analysis of any statistical report. Okay, and an analysis is not something like an equation where you plug in one number and get an answer. There is different ways you can analyze something. A lot of it comes from experience, looking at something very logically, analytically, step by step, trying to look into research behind what the graph shows, what are the numbers behind the graph, and the way it's presented too. So, looking at an example here, you have two graphs presented to you. So, Canada's population by age, according to the 2001 census. So, you have two graphs represent the same exact data, but they are displayed differently. One is in 3 dimensions and one is a 2D graph. So if you look at a 3D graph, and I sort of mentioned this earlier in the course as well, if you look at a 3D graph, it makes some parts appear larger or smaller than they actually are, right? Like, look at the slices of the chart in the back, the slices of this circle in the back, they appear a little bit smaller. They're skewed to be smaller, whereas the ones in the front, 25 to 44 age range, 24%, that appears a lot bigger, than what it should be, right? 24% represents a quarter of the entire graph, but this whole slice doesn't look exactly like a quarter, right? It's a little bit different. Whereas if you look at the 2D chart, um, by the virtue of being in 2 dimensions, you get an exact proportional relationship between each slice of the pie and their percentages. Like this blue slice actually represents 6%, whereas in the 3D graph it looks a little bit smaller. And this slice here is the biggest one here, the 24%. It looks more like closer to a quarter of the entire graph. So a 3D graph makes some parts appear larger or smaller. Than they actually are. So what we have here is something that's misleading. So someone might be trying to emphasize this 25 to 44 age group and using a eye-popping 3D chart to emphasize some kind of point that they're trying to make. Could be some other presentation. And they're trying to kind of like put the 85 and older group further in the back, kind of trying to make it go unnoticed, right? That kind of thing. Whereas the 2D graph is the better representation. It's the more fair representation of the data. So a better representation of the data. Okay, down here, look at a couple of examples. Kind of like akin to what I was showing earlier in the course with the Apple stockholder graphs. So what we have here is a problem with the scale. Okay, so here is a graph of companies' profits, annual profits versus the time. So this is a good representation of data because of the scale, whereas here the company profits, Look at the scale on the y-axis. It starts at 4 and goes to 6. Um, and so not so much about the scale, but how the graph is laid out. Like the scale is even, of course, but because it's not showing the 0 point, like it's not showing 0, it's just showing um, it's just automatically jumping to the 4, whereas a proper graph should show the 0 and show the stretch. And the reason why is because if you're showing your lowest point being the 4, the visual of the entire graph looks like there's a big, huge increase in profits and then going down. So if you were the owner of a company, well, maybe this might be nice to show to stockholders, showing, well, look at the visually how big your increase in your profits. Whereas a true graph, a more fair representation, doesn't actually shows not such a drastic increase, right? It's just a more gradual one, right, from 4 to 6 million. Whereas here it makes like 4 to 6 million looks like going from nothing to having a huge amount. Whereas here 4 to 6 million, it's an increase of $2 million, but probably at the longer trend, it's just a nice increase rather than a drastic one. So here we have a better representation on the left. And on the right, we're going to say here that by starting the graph at a point other than 0 and stretching the length of the axis, there appears to be a greater difference. There appears to be a greater difference between values. Okay, the difference meaning like from here to here. Look how big of a difference that is, right? From visually speaking. Whereas those same numbers on this graph doesn't look like it's a huge big. Doesn't look as big as a visual difference. Okay. But numerically, they're exactly the same. Right. So that's my lesson for today.